Rebounds at an angle. So these questions will involve the rotation of a plane, the inclined plane in this case, so that the inclined plane is horizontal. And the reason we do that is because if the plane is horizontal, the impulse will be experienced vertically, so the j component will change. The I component will stay the same. If we left the question as it is in its current orientation, the impulse would be perpendicular to the plane, so it would affect the I and j component, making the question more difficult. Okay, let's have a quick look through it. The diagram to start with, there are no initial and final velocities given, so I'm going to say the initial velocity before it strikes the plane is u, the final velocity is v. We also need to introduce an angle. So the angle between the horizontal final velocity vector and the plane is beta, and then the angle between the initial velocity straight down and the plane, that'll work out as 90 minus beta. So I'd ask you to work that out. I make a little bit of a leap in the solution here, assuming that point. So like I said, u is the initial velocity downwards, v is the velocity then horizontally, and what we do is we rotate the plane, so that's the diagram on the right there in the handwritten solutions, and you can see that I've labelled beta twice next to the initial speed or the initial velocity vector's magnitude. Your first step anyway is to write the vectors in I and j form. Your second step then is to assume that the impulse is in the j direction, so you use E is equal to minus v over u in the j direction, but the I component is the same. So I have the i's are equal, and I rearrange that to get me v over u, and then E is equal to v sine beta over u cos beta, and instead of the v and the u, I sub in the thing I got for the I. Bit of simplification, and we get tan beta is equal to root E. I'm not going to do part 2. All right, the next question. Again, we look at the diagram. There's no initial velocity given, and there's no velocity after the impact, so I'll be calling those u and v in this case. The angles will be the same, so there's an alternate angle, a set of alternate angles between the inclined plane, that's the theta, and the other alternate angle, or the other angle that's alternate even, is the angle between the plane and the velocity vector after the single particle rebound. So what do? We rotate the plane again so that the j component is the direction of the impulse. So the j component will change and the I component stays the same. Write the vectors in I and j form. Use what I just mentioned about the j's changing and I staying the same. We get two equations there. You sub one into the other, and we also know E is equal to 2/3, so we should be able to work that out there. Now the thing here, and this occurred for the previous question as well, the relationship between beta and alpha. So because there's a right angle between the initial and final velocity, then there's alpha plus beta will equal 90 degrees. So beta is equal to 90 minus alpha, and you can sub that into the final box there. E is equal to tan beta over tan alpha. Use a compound angle and work that out. I'll leave you finish that. Okay, and the last one we want to take a look at. In this case, we're given a speed of u. It impinges on a plane BC, and then that's at an angle of alpha. So when it impinges upon BC, the impulse is experienced perpendicular to that plane, so we need to rotate the plane clockwise through an angle alpha, so BC becomes horizontal and A comes down at an angle. So that's what the particle A comes down at an angle with a speed of u. So that's the rotation that I've made there. If the particle is travelling over horizontally with a speed of u, and then we rotate it clockwise, it means it's going diagonally down to the right at an angle of alpha, because we rotated through that angle. Same as usual, we get the initial velocity vector. We know that the I and the j components, what happens? The I stays the same, the j changes. We use E as minus v over u in the j direction, the I component stays the same. And then a little bit of algebra there. With the impulse, we're just looking at the j component. So mv minus mu, make your substitution there for the velocity vectors. The i's will have to cancel because it's the j component that changes due to the impulse, so the impulse must be in the j direction. And then all I'm going to say there is you need to write it as a vector to say that it's perpendicular to the BC plane, and the units will also be required.